So Google recently announced the Agent Development Kit, a framework for developing and deploying AI agents in multi-agent systems. In this video, I'm going to do a conceptual overview of the building blocks of Agent Development Kit, explaining how it works, what are the components, and what are its uses. So let's start with the definition. The Agent Development Kit is a flexible and modular framework for developing and deploying AI agents. ADK can be used with popular LLMs and open source generative AI tools, so it's not really tied specifically to the Google AI ecosystem, but it is designed with a focus on tight integration with the Google ecosystem and the Gemini models. To better understand where ADK kind of fits in the ecosystem, it's useful to understand about levels of abstractions when talking about agents. So the first level, which is no abstractions, is the DIY or do-it-yourself type of agent applications, where you build an agent from scratch using lower level APIs like LLM calls, function calling, etc. The first level of abstraction is a low level LLM framework like LangChain. You get some basic abstractions for common language processing tasks like parsers, splitters, and prompt templates. There's still, however, a fair amount of work for a developer to do, a little bit of a learning curve as well, as you'd have to learn things like the LangChain expression language, for example. Next up is a low-level orchestration framework, where there are greater abstractions around working with LLMs, and instead you focus on the orchestration logic. LangGraph is a good example of this, where you can build graphs to design your agentic workflows. It's one level of abstraction higher than LangChain. You don't have to deal, for example, with parsers, splitters, or writing your own React reasoning loop to build an agent. Instead, you deal with higher level constructs like an agent node and tools. However, it's still somewhat low level because you're working with graphs and nodes and edges as opposed to actual agents. LangGraph code is difficult to read and reason about if you didn't write it yourself. The next level is then that of an agent framework. This is where Agent Development Kit fits. It's also incidentally where the OpenAI Agents SDK, also recently released, would fit in. The fact that there are a lot of similarities between these two frameworks speaks to the fact that the industry is converging on what the key set of abstractions should be for building agents, and that is above graphs and at the level of agents, tools, and things like session management and callbacks. By the way, there are other frameworks in this category like Crew AI, for example. Finally, there's of course level 4, which is for no-code tools, kind of ready-to-use solutions, and there are a handful of options there, giving people a lot of abstractions and no coding skills required, but also the least amount of flexibility. Okay, with that understanding, let's start talking about the concepts in the Agent Development Kit, starting with the agent. So an agent is a self-contained execution unit designed to act autonomously to achieve specific goals. There are 3 categories of agents in ADK. LLM agents. These agents use LLMs as their core engine to understand language, reason, plan, generate responses, and more importantly, to dynamically decide how to proceed or which tools to use. This puts the LLM in control of the execution flow. Then we have workflow agents, which operate based on the predefined logic or deterministic pattern, which could be sequential, where basically it's a chain of LLM calls in sequence. In this case, the sequential agent is the workflow agent that executes the sub-agents, if you will, in the order that they are specified in the list. There's no LLM in this workflow sequential agent. The sub-agents may or may not use LLMs and tools, but the sequential agent itself is simply a deterministic workflow. The other pattern that a workflow agent can implement is the parallel agent. As the name implies here, we're just simply running subtasks or sub-agents in parallel as opposed to sequentially. And then we have the so-called loop agent, which is the third category of a workflow agent. And this one can run a sequence of agents in a loop for a specified number of iterations or until some termination condition is met. Okay, so the third and final category of agents is a custom agent. This is a catch-all basically to anything else you may want to build, which could be more complex workflows that, for example, combine sequential executions with parallel executions. There's maybe an LLM deciding when to invoke what, maybe taking different paths based on runtime conditions. So basically any kind of custom or more complex workflow, it would be a custom agent here. The Agent Development Kit supports building sophisticated applications also by composing multiple distinct agent instances into a multi-agent system, often forming a hierarchy like this one here with a root agent and child agents. And this is something you might want to do to enhance the modularity of your overall system and potentially improve performance by having more specialized agents that do one specific task well. Alright, so how would you instantiate an agent in the ADK? And it is as simple as creating an agent object with a model, a name, and system instructions. Okay, the next concept is that of a tool. A tool represents a specific capability provided to an AI agent that enables it to perform actions and interact with the world and so on. And typically you define a set of tools and provide it to the agent, and invoking that agent will result in the ADK framework executing the flow that you see here. So first it will invoke the LLM with the tool specifications. Then the LLM will output a function call result, provided that it decides a tool should be used for the given user query. Then the framework executes the tool directly and passes the output back to the LLM. And then the LLM processes the results and the agent will produce the response to the user or whatever the next action is. There are three types of tools you can work with. The built-in tools. These are ready-to-use tools provided by the framework, and these are from Google. So it would be, at the time of recording, Google search, code execution, and retrieval augmented generation tool. Then there are third-party tools, which allows you to integrate some out-of-the-box tooling, for example, from LangChain tools, Crew AI tools, and so on. And there are the function tools, which are basically the ones you create. Technically, a tool is typically just a modular code component, like a Python function or a class method. And all you have to do to create a tool, a function tool that is to implement that function and wrap it around the function tool object, as you see here. Then to pass the tool to the agent, you just pass it in the tools attribute of the agent class. And you can obviously provide more than one tool as well. A special type of tool is the agent tool, where we specify an agent as a tool. It all works the same way. The difference is that instead of the framework now invoking a piece of code that you created, it will invoke an agent that you created with the framework itself. And you can call it a sub-agent, if you will. Typically, this would be something very specialized to a specific task. And after invoking that agent, the framework will pass the response back to the main agent. And one other special type of tool is a long-running function tool. This is a piece of code again, but this one is expected to take some time to run, but be able to return intermediate results to keep the model and user informed about the progress. The way it works is that you create a Python generator function, a function that uses the yield command that you see here, and the framework will take care of showing those intermediate results, for example, in the form of a Python dictionary, back to the LLM, packaged within a function response object. When the generator completes, the framework sends the return value as the content of the final response object. Let's now talk about the conversational context concept. There are three components here: a session, state, and memory. Let's break it all down. So the session corresponds to the current conversation thread. It's the history of the interaction between a user and your agent system with a chronological sequence of messages and actions. Let's talk about the components of a session. The session object has, first of all, an identification, which comprises of an ID, an application name, which identifies the agent application, and an user ID, which links the conversation to a particular user. Then there's the history. This is the core of the session. It contains a sequence of events corresponding to the interactions. We'll talk about events shortly. There's the session data or state, which stores temporary data relevant only to this specific ongoing conversation. More on that in just a second. And finally, we have an activity tracking component or last update time, which is a timestamp indicating the last time an event was added to this thread. The framework provides different implementations for the session service, which is the service that handles sessions. The first is the in-memory session service. As the name implies, that keeps all data in memory. This is convenient and the easiest to get started with, as you don't need to implement any storage infrastructure, but the caveat is that it doesn't offer any persistence, because it's in memory. Here's how you would use it. Just instantiate the in-memory session service, and you're good to go. Okay, next is the database session service, which is backed by a relational database and therefore offers persistence. The framework uses the SQL Alchemy library as the database client, and it works with a variety of database engines. Here's how you would use it. You instantiate the database session service with the database URL. In this example here, we are using a local SQLite database file. Finally, there is the Vertex AI session service, which will use Vertex AI infrastructure to implement the session storage. It offers persistence and also high availability. To use it, you need to instantiate the Vertex AI session service class with the Google Cloud Project ID and Google Cloud location for the storage. And you need to be hosting your agent app in Agent Engine, formerly known as Reasoning Engine, for this to work. Alright, so we talked about sessions and we briefly mentioned state as one of the components of the session. Think of the state as the session scratchpad. It's essentially a dictionary with keys being strings, values being anything serializable, and that works as basically a temporary state to hold on to for the duration of a conversation. To have the LLM access the state, you can simply put the state key inside curly braces in your prompts. As you see in this example here, we have customer info and current date as two keys in our state dictionary, and we are injecting their values into the prompt for the model. Note that the framework is taking care of that. To access the state, you can just grab the state attribute from the session service. Fairly straightforward. But here's a warning. Avoid directly modifying the state in the object. State updates should be handled through events. Let us talk about events before we move on to memory, which is the final conversational context component. Okay, so to understand the right way of updating state, we need to talk about the concept of an event. An event in ADK is an immutable record representing a specific point in the agent's execution. An event can be user messages, agent replies, requests to use tools or function calls, tool results, state changes, control signals, and errors. Events are a central concept in ADK because they serve as the standard message format between the user interface, the runner, agents, LLMs, and tools. Everything flows as an event, including state changes. So here's an example. If you want to, say, set the task status in your state to active, you create a dictionary with that specific change. Then you create an event action with the state delta attribute set to the dictionary. Then you create the event object with the event action in there. And you use this session service to append the event to that session. The session service is then the one responsible for handling and storing that state in a way that is thread safe. Okay, now the last building block of conversational context is memory. While sessions allow us to track the history and temporary data for a conversation, memory is about long-term storage so that we can remember, for example, past conversations. So memory is like a searchable archive or knowledge library that the agent can consult, potentially containing information from many past chats or other sources. There are also a couple of implementations for the memory service out of the box here. We have in-memory memory service, which stores everything in memory. Evidently not recommended for production, as you wouldn't actually get persistence here, which is the whole point of memory. But it's useful as a way to quickly prototype an agent. Here's how you instantiate it. Then there's Vertex AI RAG memory service, which uses the Vertex AI RAG service. So here again, we're relying on Vertex AI infrastructure, which is highly available and scalable. This is a vector-based storage, so it can scale to data that goes well beyond the LLM context window, but recall may suffer if you have a lot of data in there. Here's an example of how you would use it. You specify a RAG corpus resource name, some RAG hyperparameters here, and you instantiate the Vertex AI RAG memory service. Alright, next, let's talk about the concept of an artifact. An artifact is essentially a piece of binary data, like the content of a file, for example, identified by a unique file name string within a specific scope, which could be session or user. Each time you save an artifact with the same file name, a new version is created. So artifacts are not stored directly within the agent or session state. Their storage and retrieval are managed by a dedicated artifact service, which can be in-memory artifact service or the GCS or Google Cloud Storage artifact service. As you can imagine by the names here, one stores the artifacts in memory, the other backs them up in Google Cloud Storage for persistence. Another key concept of ADK is that of callbacks. A callback is a way to inject some code execution at specific points of the execution flow. The code can be anything you want, you just need to define them, and the framework will automatically call them. You can define when the callback should be invoked by choosing one of 4 different types. A before agent callback, which will run before the agent's main processing logic runs. An after agent callback, which will run after the agent's main processing logic runs. After or before model callbacks, which will execute after you receive a response from the LLM or before you invoke the LLM, respectively. And finally, after or before tool callbacks, which will run after or before a tool is invoked. Now, what are callbacks useful for? There are a couple of good uses for it. For example, login observability if you want to log detailed information at critical steps, customization and control of the overall workflow. If, for example, you want to bypass a step, like not invoking a tool based on a certain condition, or to implement guardrails and enforce safety rules, inspecting the input or output of a model, for example, for harmful language or personal information. And you could use it also to manage state. Callbacks are an excellent way to create a state modification event if you want to inject some external context into the model, like at what step of the workflow it is at, or some other dynamic information it needs to know. You can register callbacks by passing your defined Python functions as arguments to the agent's constructor. Now note these special context objects passed to the callback function here. The framework automatically includes these objects with contextual information like invocation details, session state, and potentially references to services like artifacts or memory. Another thing to note is that you can either return a none, in which case it will allow the workflow to proceed as usual, or you return a specific object which will override the default behavior of whatever the next step of the workflow would be. So exactly how you override the behavior will depend on the type of callback. If it's a before model callback, for example, like this one here, it means that we will skip the call to the LLM, and instead, whatever we return in this callback function will be given as a response instead. Okay, so let's talk about different types of context. Invocation context provides access to the entire state of the current invocation. This is the most comprehensive context object. Then there's read-only context, which is provided in scenarios where only read access to basic information is needed and mutation is disallowed. Next is callback context. We already mentioned this one briefly before. This is passed as callback context to agent lifecycle callbacks and model interaction callbacks. And the purpose here is to facilitate inspecting and modifying state or interacting with artifacts and accessing invocation details, specifically within callbacks. Right, finally, we have tool context, which provides everything callback context does, plus specialized methods essential for tool execution, like handling authentication, searching memory, and listening artifacts. Alright folks, we're almost done. The next concept here is evaluation, which is of course a critical one. At a high level, you provide the framework with expected results for given user queries. That would be your ground truth dataset. And you run the agent with those queries, and we compare the results and compute certain metrics. So how exactly does that work? Since we're talking about agents, we need to think about trajectory and tool use. So a trajectory is the sequence of steps that the agent takes. For example, a series of tool calls. We'll then compare that with a ground truth trajectory using one of the methods that you see here. It could be an exact match comparison where we expect an exact trajectory the way we defined it, or it could be an in-order match, which allows for extra actions to be taken by the agent, but whatever actions are executed are done in the right order. Any order match where we say we don't care about the order or whether there are extra actions as long as the required actions are there. Then there's the more classical metrics of precision and recall, and single tool use, which you can think of as a unit testing for tool use. So checking if the model is employing a given tool correctly. Now there are two approaches to specifying your ground truth. You can use a test file. This would be akin to creating unit tests, for example, with more basic, simpler interactions. Or you can use a more elaborate eval set file, which is similar to the test file, but this one will contain example end-to-end interactions. It may contain multiple lengthy sessions, making it ideal for simulating more real-world multi-turn conversations. This is more suited for integration tests, which are run less frequently than unit tests due to their more extensive nature and also costs involved. You then specify the evaluation criteria, which define how the agent's performance is supposed to be measured against the evaluation dataset. So you can choose a tool trajectory average score, which will compare the agent's actual tool usage with the expected tool usage, average all the results, and provide a score, or response match score, which compares the agent's final response with the expected final response and uses the root metric to calculate the similarity between the responses. Here's an example configuration file that specifies the evaluation criteria. So how do you go about doing evaluations with the framework? You have basically three options. As a developer, you can use the web-based UI, which you can launch by running ADK web, or programmatically with PyTest, for example, and run it as you would any other unit or integration test. Or using a command line interface, which you can run with ADK eval to run evaluations on an existing set directly from the command line. Alright, one final concept. The ADK runtime is the underlying engine that powers your agent application during user interaction. This is the system that takes your defined agents, tools, and callbacks and orchestrates their execution in response to user input, managing the flow of information, state changes, and interactions with external services like LLMs or storage. So think of the runtime as the engine of your agentic application. You define the parts, and the runtime handles how they connect and run together to fulfill a user's request. So the runtime operates on an event loop, which goes more or less like this. The runner receives a user query and asks the main agent to start processing. The agent and its associated logic will then run until it has something to report, like a response, a request to use a tool, or a state change. It will then yield an event back to the runner. The runner receives the event, processes any associated actions like saving state changes via services, and forwards the event onwards to the user interface, for example. Only after the runner has processed the event does the agent's logic resume from where it paused, now potentially seeing the effects of the changes committed by the runner. In the documentation here, you can see a flow diagram that illustrates a simplified invocation of the ADK, and that might give you a better sense of what is going on exactly in that runner component, how the messages are passed through by the different components, and it could be a useful way to get a better sense for how the framework works on a lower level. Alright, that's it for this video. I really just wanted to break down the components here from a conceptual overview perspective. I hope to make a future video soon where I'm gonna actually do some hands-on demos and tutorials for actually working in code with the ADK. Thank you for watching.